There's a signal arriving at Earth right now that left its transmitter almost 20 hours ago. It came from a machine built with 1970s technology, 13 billion miles away, drifting through a region that no human instrument had ever touched until 8 years ago. And the numbers inside that signal are wrong. Not corrupted. Wrong in the sense that they don't match what physics said they should be. The space between the stars turned out to be far hotter than the models predicted. The magnetic field out there is pointed in a direction nobody can fully explain. And the boundary Voyager 2 crossed to get there behaves less like a wall and more like something breathing. Scientists have had those measurements for years now. They still can't explain them. And the one instrument that had the best chance of answering the biggest question was switched off in 2024 because there wasn't enough electricity left to keep it running. Let's start with what's actually happening physically at this moment. Voyager 2 is roughly 13.2 billion miles from Earth. In the units astronomers actually use, that's about 143 astronomical units. 143 times the distance between the Earth and the Sun. It's moving away from us at something like 34,000 miles per hour. And it has been moving that fast, without stopping, without slowing, without a single course correction that mattered, since Ronald Reagan's first term. Its radio transmitter puts out about 20 watts. That's a dim household bulb. That 20-watt whisper spreads out across 13 billion miles of vacuum. And by the time it reaches Earth, it is so faint that it takes one of the giant 70-meter dishes of NASA's Deep Space Network. Antennas the size of apartment buildings in California, Spain, and Australia, just to notice it at all. And when a controller at the Jet Propulsion Laboratory sends a command up to the spacecraft, they wait almost 20 hours for it to arrive. If they want to know whether it worked, they wait another 20. 40 hours, round trip, to ask a machine a single question. That's the working reality of this mission now. Conversations that take 2 days. Voyager 2 launched on the 20th of August 1977 on a Titan 3E Centaur, 16 days before its twin. It flew past Jupiter in 1979, Saturn in 1981, Uranus in 1986, Neptune in the summer of 1989. And it remains, to this day, the only spacecraft that has ever visited either of those last two worlds. Everything humanity knows about Uranus and Neptune from close range, we know because of one afternoon in 1986 and one night in 1989. Then the planets ran out. And that's usually where a mission ends. The science team writes the final report, the funding winds down, the spacecraft becomes a piece of hardware nobody talks about. But the Voyagers were still healthy, still pointed outward, still carrying instruments that could measure charged particles and magnetic fields. So NASA renamed the whole thing the Voyager Interstellar mission and just let them keep going. Nobody involved seriously expected to still be doing this in 2026. Now, the part that matters. On the 5th of November 2018, at a distance of about 119 astronomical units, Voyager 2's instruments recorded something that took less than a single day to happen. The plasma streaming past the spacecraft. The thin, electrically charged gas that had been blowing outward from the sun for the spacecraft's entire life. Slowed, and then stopped registering as solar material at all. The count of low-energy particles from inside our own system dropped off a cliff. At the same time, the count of high-energy cosmic rays from the wider galaxy jumped. Voyager 2 had crossed the heliopause. It had left the bubble. And here I need to be precise about what that means, because this is the single most misunderstood fact in this entire story. The sun does not simply sit in space, it blows. A constant supersonic wind of charged particles streams off it in every direction. And that wind carves out an enormous cavity in the gas and dust that fills the galaxy. That cavity is the heliosphere, a bubble of the sun's own material with all 8 planets, every asteroid, every comet you've ever seen sitting comfortably inside it. The heliopause is the skin of that bubble. It's the place where the outward pressure of the solar wind finally loses to the pressure of the interstellar medium pushing back. Crossing it does not mean leaving the solar system. Voyager 2 is still gravitationally bound to the sun. It hasn't reached the Oort cloud, the vast shell of icy bodies that marks the true outer edge of the sun's domain. And it won't reach even the inner boundary of that for roughly another 300 years. Passing all the way through it would take tens of thousands. But it has left the sun's atmosphere in the most literal sense. It is now sitting in raw galactic material. Gas thrown off by the deaths of massive stars millions of years ago, drifting between the stars, unmixed with anything from home. That is the place no human instrument had ever directly sampled before Voyager 1 got there in 2012. And Voyager 2's crossing mattered even more than its twins, for one specific and slightly heartbreaking reason. Voyager 1's plasma instrument, the device designed to measure the temperature, density, and speed of that charged gas directly, broke in 1980. It had been dead for 32 years by the time Voyager 1 crossed the boundary, so Voyager 1 arrived in interstellar space essentially unable to taste it. It could infer, it could measure indirectly, but it couldn't take the reading that everyone actually wanted. Voyager 2's plasma instrument, built by a team at MIT, was still working perfectly, which means that on that day in November 2018, for the first and so far only time in human history, we got a direct in-place measurement of the plasma at the edge of the solar bubble and just beyond it. So what did it say? The first surprise came before the crossing, not after. For about a year and a half of travel, a region roughly 1.5 astronomical units thick, wider than the distance from Earth to Mars, the plasma ahead of Voyager 2 started behaving strangely. It slowed down. It heated up. Its density roughly doubled compared to normal conditions inside the bubble. The spacecraft was, in effect, driving into a pileup, material from the sun stacking up against the wall it couldn't get through. Then, much closer in, about 6/100ths of an AU before the boundary, a second, much thinner layer, where the flow slowed again, the density climbed again, and the magnetic field strengthened. And then the crossing itself, in under a day. On the other side, the electron density jumped enormously. The plasma wave instruments on both Voyagers measured the interstellar gas as far denser than the solar wind they'd been swimming in. That part, scientists had predicted. That part was fine. The temperature was not fine. Voyager 2 measured the interstellar plasma at somewhere between 30,000 and 50,000 Kelvin. The models, decades of careful theoretical work, backed by remote observations, had said 15 to 30,000. The real thing came in hotter than the ceiling of the prediction. Now, one clarification, because this fact gets mangled constantly online. That does not mean the spacecraft is roasting. Temperature in physics describes how fast individual particles are moving. It says nothing about how many of them there are, and out there are almost none. The gas is so thin that the total heat energy actually touching the spacecraft is negligible. Voyager 2 is freezing. Its engineers spend a genuinely worrying amount of effort keeping it warm enough not to seize up. But the particles themselves are moving far faster than anyone expected. The leading explanation is that this isn't pristine interstellar space at all. It's compressed and disturbed interstellar space, gas that has been squeezed and heated by its own collision, with the sun's magnetic field piled up outside the bubble the way water piles up in front of a ship's bow. If that's right, then both Voyagers are still sitting in a transitional zone, a kind of disturbed shoreline, and true undisturbed galactic space is still somewhere further out. That is a hypothesis. A good one, consistent with the data, but it is not settled and no one has been able to model the full picture. The second surprise is stranger, and to me it's the most quietly unsettling result of the whole mission. Voyager 1 had found, back in 2012, that the magnetic field just outside the heliopause was pointed in almost the same direction as the magnetic field just inside it. That shouldn't happen. Inside the bubble, the field is the sun's, wound up by the sun's rotation into a spiral, carried outward by the solar wind. Outside, the field belongs to the galaxy, two completely independent systems, with no obvious reason to agree on anything. Finding them aligned is a bit like walking out of a building during a storm and discovering that the wind outside is blowing in exactly the same direction as the air conditioning inside. When Voyager 1 reported it, there was a reasonable escape hatch. One measurement, one location, one moment in time. Maybe it was a coincidence. Maybe Voyager 1 had crossed at an unusual spot. Then Voyager 2 crossed 6 years later in a completely different part of the sky, in a totally different phase of the sun's activity cycle, and measured the same alignment. Two independent samples, same result. Which strongly suggests it's a real feature of how our bubble sits inside the galaxy and not a fluke. Nobody has a complete explanation for why. The third surprise is about leakage. The heliopause is not a sealed membrane. Both spacecraft found material crossing it in both directions. Voyager 1, on its way out, ran into what looked like tubes of interstellar magnetic field that had pushed into the sun's territory weeks before the actual crossing. Early warning signs, a leak inward. Voyager 2 saw no such precursors at all. What it found instead was on the other side, a layer just beyond the boundary where low-energy particles born inside our own solar system, were streaming outward along the magnetic field lines, escaping into the galaxy. And within that layer, the galactic cosmic ray count was slightly suppressed, running at about 90% of the level measured further out. So one spacecraft found the galaxy leaking in, the other found the solar system leaking out. Same boundary, two crossings, opposite behavior, which tells us something important and slightly humbling. This is not a fixed structure that we've now measured. It's a dynamic, patchy, constantly shifting interface, and each Voyager sampled a single point of it at a single moment. We have 2 pixels of an enormous moving image, and here's the detail that surprised the veterans on the team more than any of it. Voyager 1 crossed the heliopause near the peak of the sun's activity cycle. Voyager 2 crossed near the minimum, a completely different pressure environment, 6 years apart, in different directions. The solar wind's push should have varied. The bubble should have been inflated in one case and deflated in the other. The 2 spacecraft should have hit the wall at noticeably different distances. They crossed at almost exactly the same distance from the sun. One of the mission's most senior scientists said plainly that they don't understand why that is. Not, here's our best theory. They don't know. Nearly half a century of solar physics and the boundary of our own solar system sat where it wasn't supposed to. There's one more thing Voyager 2 has been doing since 2018 that I find genuinely eerie, and it only became visible because the spacecraft kept living long enough to see it. The sun's influence doesn't actually stop at the heliopause. Big eruptions on the sun send pressure waves outward through the solar wind. Those waves travel for months, sometimes more than a year, until they slam into the inside of the bubble. And some of that energy keeps going. It transmits through the boundary and out into the interstellar medium beyond. Voyager 2, sitting out there in supposedly foreign territory, has recorded at least 2 major compression waves and a shock front passing over it since it crossed. Ripples from our own star, arriving in interstellar space long after they left home, washing over a spacecraft that had already left. And even here, the 2 Voyagers disagree. The disturbances Voyager 2 measured look smoother and more wave-like than the sharper shocks Voyager 1 recorded. When Voyager 2 made its crossing, it registered unusually strong magnetic fields, possibly because it went out through the southern side of the heliosphere, where the material outside may be more compressed. And one of the major shocks Voyager 1 detected never showed up at Voyager 2 at all. To date, no model has managed to reproduce all of those observations together. That's not a failure of science. That's what the frontier actually looks like from the inside. Messy, partial, and full of results that don't yet fit. Which brings us to the part of this story that is, honestly, a slow-motion tragedy with a very precise timeline. Voyager 2 has no solar panels. At its distance, sunlight is useless. The sun is just a particularly bright star. Instead, it runs on 3 radioisotope thermoelectric generators, devices that convert the heat of decaying plutonium into electricity. Plutonium decays on a fixed schedule. Nothing anyone does can change that. The spacecraft loses roughly 4 watts of available power every single year, and it has been losing 4 watts a year since 1977. 4 watts sounds like nothing. But there's nothing left to take it from. Over the decades, engineers have shut down cameras, heaters, and entire subsystems. They've turned off the warmers on instruments and then watched, holding their breath to see whether the hardware survived being frozen. Sometimes it did, at temperatures far below what it was ever rated for. That's not clever design so much as extraordinary. Luck compounded over 50 years. But the real cuts have come recently, and they've come fast. In late September 2024, they switched off the plasma science instrument. That instrument. The one that had been running since launch. The one built at MIT, the one that had given us the only direct measurement ever taken of plasma at the edge of the solar bubble, the one whose twin died in 1980, went silent after 47 years of continuous operation. The scientist, who had spent decades of his career on it, described losing it simply as sad. In March 2025, they turned off the low-energy charged particle instrument. 3 instruments remained: the magnetometer, the plasma wave subsystem, and the cosmic ray subsystem. And the plan on the books said one of those 3 had to go before the end of 2026. Then, this August, the engineers pulled off something that genuinely deserves to be remembered. They call it the Big Bang, a maneuver a year in the making involving nearly the whole team. The idea was to send a set of commands that would simultaneously switch off certain powered components and switch on lower consumption alternatives that could do the same jobs. Do it wrong, and you either lose the science or you let the spacecraft get too cold to function. Get it right, and you free up enough electricity to keep everything running. They got it right. Voyager 2 has enough power to keep all 3 of its remaining instruments alive for at least another year. NASA plans a similar operation on Voyager, one in the coming months, and there's some hope it might even allow an instrument that was shut down in April to be turned back on. Think about what that took. Commands written for computers with memory measured in kilobytes. Documentation from the 1970s, some of it written by engineers who have since died. A 40-hour delay between asking and knowing. And the whole thing had to work first time. But the Big Bang buys time. It doesn't buy a solution. The plutonium keeps decaying. The 4 watts a year keep vanishing. The current expectation is that at least one instrument might survive into the 2030s. The Project Scientist has put it in a way that stays with you. Every day out there is a day in territory no spacecraft has ever occupied, which means every day could be the last one. And equally, every day could bring another revelation. Here's the cruel arithmetic underneath all of it. The further Voyager 2 travels, the more scientifically valuable every single measurement becomes, because it's moving deeper into that disturbed transitional region and closer to whatever genuinely undisturbed interstellar space looks like. The data gets better as the spacecraft gets weaker. The most interesting readings of the entire mission may lie just beyond the point where the power runs out. And there's nothing behind it. No approved mission is currently on its way to replace the Voyagers. Concepts for a dedicated interstellar probe have been studied seriously, but studying a concept and launching one are separated by decades and billions of dollars. Even if such a spacecraft launched tomorrow, it would need something like a human generation to reach the boundary. So when the last instrument on Voyager 2 goes quiet, the direct measurements stop. Not paused, stopped. Possibly for 50 years, possibly longer. Everything we learn about the edge of our own bubble after that will come from models, from remote sensing, and from the archive of data these two machines managed to send home while they still could. And then Voyager 2 keeps going anyway. It doesn't need power to travel. It only needs power to talk. Once the transmitter falls, silent, the spacecraft carries on at 34,000 miles per hour, in the same direction, essentially forever, through the Oort cloud over the next several hundred centuries, and then out into the open galaxy. NASA's projections put it passing within roughly 1.5 light years of a small red dwarf star, called Ross 248, in about 40,000 years. Not a visit, not an encounter, just the closest it will come to another sun in the next 400 human civilizations worth of time. It's still carrying the golden record. Greetings in dozens of languages, whale song, a Bach prelude, photographs of a planet as it looked in 1977, bolted to the side of a machine that will outlast every structure ever built on Earth. But the record isn't really the point anymore, and I'd argue it never was. It was a gesture. What Voyager 2 is actually doing is far less romantic and far more remarkable. It is sitting in a place we cannot otherwise reach, sending back numbers, and those numbers keep refusing to behave. The gas out there is hotter than it should be. The magnetic fields line up when they have no reason to. The boundary sat in the same place under conditions that should have moved it. Waves from our own sun are still catching up with a spacecraft that left the sun's territory 8 years ago. Every one of those results is a question that has been asked and not yet answered. The strange thing is that all of them were found by accident. None of them were the mission. In 1977, this was a 5-year trip to look at Jupiter and Saturn. Nobody designing those instruments imagined they'd be used to measure the wall at the edge of the solar system, because in 1977 no one was sure that wall could be reached at all. We got there because two machines refused to stop working, and because a small group of people kept finding ways to give them one more year. That's the situation right now. Voyager 2 is still out there, still cold, still counting particles, still spending its last watts on a conversation that takes 40 hours to complete, and it's still telling us things we can't explain yet. The only real question left is how much it manages to say before the power runs out, and whether when the answer finally arrives, there'll still be anything listening on the other end.